All right, we are recording, and now we are in section 11.6. This deals with directional derivatives and the gradient vector. So I think the introductory example is pretty nice, or the scenario. The weather map in figure 1 shows a contour map of the temperature function for the states of California and Nevada at 3 p.m. on a day in October. So here is the contour map, and you know how a contour map works. Those are level curves that they are showing, and with different degree temperatures. Now, Los Angeles is south, and then you can see Reno, San Francisco's north. To the east we have Las Vegas. So, okay, let's continue here. Now, the partial derivative, t, the temperature function is a function of x and y. Okay, so, the map is a two-dimensional map, right? And different locations, the coordinates, the different locations depend on x and y coordinates. X coordinates would tell you, it would give you a measure in terms of east-west, and the y-coordinate would give you a measurement in terms of where you're located in terms of like north or south. But of course, when we take the partial derivative with respect to x, so it says there the partial derivative t sub x. Okay, the partial derivative of t with respect to x at a location such as Reno is the rate of change of temperature with respect to distance if we travel east from Reno. Okay, so remember, partial derivatives with respect to x are how the function, it's the rate at how the function changes, okay, as we move in the direction of the positive x-axis. Now, the t sub y, the partial derivative of t with respect to the y, is the rate of change of temperature if we travel north. So the partial derivative of t with respect to y is the rate of change of the temperature as we move in the positive direction, in the y-axis direction, which is in positive y-axis is the northern direction. So this makes absolute sense. We can find temperature, the rate of temperature, rate of change of temperature at any location with respect to moving east or north using the partial derivatives that you have learned. But what if we want to know the rate of change of temperature when we travel southeast, okay, towards Las Vegas or in some other direction? Okay, there is a rate of change of temperature in the southeast direction, in the northeast direction, in any direction. And so in this section, we have to introduce a type derivative that can deal with this called a directional derivative. Okay, and maybe I will highlight it here. Right, so the directional derivative enables us to find the rate of change of a function of two or more variables in any direction we want to go. So how does this work? How would this work? Well, let's first of all remind ourselves how the partial derivatives with respect to x and y were defined. Okay. I mean, we learned these definitions. The partial derivative with respect to x means you hold the y variable constant and let x change. The partial derivative with respect to y means you hold the x variable constant and let y change. Now what we want to do is let there to be change in any direction we want. So the scenario we're talking about is what we're seeing in figure 3. Okay, this is a beautiful picture in section 11.6, and you have this surface S, okay, and you have, the surface S is represented by a function, Now let me just, one moment here. So Z is a function of X and Y. And that's this blue surface S. And if we consider a point P on the surface that has coordinates x sub 0, y sub 0, z sub 0, and that pink tangent line points in the direction of the vector u in the plane below. So see the vector u, which we assume is a unit vector, that vector u in the plane below points in a certain direction. Well, on this surface, at the point with coordinates x sub 0, y sub 0, z sub 0, we draw a tangent line to the surface that also points in that direction of the vector u, right? Well, in terms of like the horizontal movement, it points in the direction of the vector u. But in other words, think of it like this. The vector u appears to be pointing, if we think of like in terms of east, west, south, north, the vector u appears to be pointing in the north eastern direction. So the tangent line, that pink tangent line on the surface, it slopes downward, but it's oriented in the direction of the northeastern direction, you see? And there's some slope for that tangent line. And the question is, how do we find the slope of that tangent line? Well, so if you look in where that vector u is, you have a h, which is part of the definition of a derivative. We let h go to 0. And you have, the vector u has, think of the vector u as having coordinates a, b. And then you multiply the vector u by h. That's, as you let h go to 0, that's going to bring that vector h times u is going to get smaller and smaller as you let h go to 0. And so the secant line that connects points P and Q approaches the tangent line T. So it works just like you learn the directional derivative. Well, the partial derivative that you learn is either a slope of a tangent line to the surface in the positive x direction or positive y direction. Okay, depending on which partial derivative you're talking about. The directional derivative gives a tangent line in direction that the vector u points. And the vector u, we're assuming that to be a unit vector. So formally speaking then, here is, if we were to try to find the directional derivative, this is the definition. So capital D stands for directional derivative. So we're looking for the directional derivative of a function when x equals x sub 0, y equals y sub 0, in the direction of the unit vector u. That is the limit as h goes to 0 of this quotient. And you see how now you're letting x and y both vary. And they're varying according to the components of the vector u. Now that would be, we could use this definition to find values of the directional derivative, but it actually would be somewhat complicated, right? So fortunately, there is an easier way to find a directional derivative. That definition, well, that's actually proven. Here is the formula that we're going to be using or can use to find the directional derivative. The directional derivative of a function in the direction of any vector u is equal to this linear combination of the partial derivatives with respect to x and with respect to y. Okay, so, and the linear combination, the weights, are the components of the vector u, the component A and the component B. Okay, so to see this, to have a feel for it, let me go ahead to the whiteboard and give you a helpful example to see this, to help you feel. I want to give you an intuitive feel for this. So let's see here. Let's leave that. Okay. So, all right. Here's the definition of the directional derivative. They prove it in the book, but it equals A times the partial derivative of f with respect to x plus B times the partial derivative of y. I'm sorry. The directional derivative equals A times the partial derivative of f with respect to x plus B times the partial derivative of f with respect to y. And by the way, this is where u is equal, has components A and B. And this is a unit vector. So if we think of, one moment here. Okay, so if we think, hold on here, of an x-axis and a y-axis, and then we, for instance, were to draw some vectors, that could be a vector, that could be a vector, this could be a vector, right? They all could be vectors. This vector here goes to point 1, 0. Okay, that could be, for instance, our unit vector. Unit vector could be this vector. That could point to 0, -1. Maybe that's our unit vector. Okay. This point here, could this point here be -1, 1? This point here? Would that be correct? Could our unit vector be -1, 1? Is that allowable? Well, does the vector u point in the direction of -1, 1 about? Does it look like it points in the direction of -1, 1? It does, right? But is that a unit vector? No. you have to divide by square root of 2. Okay, so like for example, let's say that you wanted the directional derivative of a function in the direction of the vector 0, 1. And of course, we're going to utilize this formula here. Okay, that's going to equal something times the partial derivative with respect to x plus something times the partial derivative of f with respect to y. What's going to go? What are the weights going to be? What are A and B going to be in this situation? That's right, Lexi. 0 and 1. And actually, hold on. You're right. I actually want to make that, I want to change that. Hold on. Instead of 0, 1, let's say I had 1 and 0. 1 and 0. What are the weights going to be then? So I'm looking at the slope of the tangent line to the surface at a point, looking in the direction of this unit vector here at 1, 0. What are the weights going to be? What's the weight that goes in front of the partial derivative of f with respect to x? That's right, Norino, 1, because A equals 1. And then 0 would go in front of the partial derivative of f with respect to y, because b equals 0. So this is just going to give you the partial derivative with respect to x, which is what we would want. If we are finding, remember, directional derivative is the slope of a tangent line to a point on the surface where that tangent line is pointing in any direction you want. Well, if the tangent line is pointing in the direction of the positive x-axis, the unit vector is 1, 0, and so of course we want to get the partial derivative of f with respect to x. What if you had the directional derivative where the unit vector is 0, 1? Now you're looking at the slope of the tangent line to a point on the surface where the tangent line points in the direction of the positive y-axis. So what are your weights going to be there? What do they have to be? Who thinks they can give an answer? It's a weighted average of the partial derivatives. That's right, Mary. It's going to be 0 and 1. And so you're going to end up getting the partial derivative of f with respect to y, which is what you want. I mean, this directional derivative formula needs to give us the slopes of tangent lines in the directions that we already learned, which is with respect to the x-axis and the y-axis, and those are the partial derivatives. Now, let's do one more here. Let's say you wanted to know the directional derivative. Let's say I'm focused on this unit vector here. I'm highlighting in green, where the unit vector is -1 root 2 and 1 root 2. What are the weights going to be in that case? What are the weights for the partial derivatives? What weights are going to go, or coefficients are going to go in front of the partial derivatives? That's right, Angela. Very good. Very good. -1 over root 2 and +1 over root 2. And as another example, if you wanted to find the directional derivative of a function where your unit vector is, I mean, 1 root 2 and 1 root 2, this unit vector is halfway between the x-axis and the y-axis, right? 1 root 2 comma 1 root 2, that unit vector is halfway between the x-axis and the y-axis. And if you, hold on here, if you compute the directional derivative for that, you're going to get 1 over root 2 times the partial derivative with respect to x plus 1 over root 2 times the partial derivative of f with respect to y. So essentially, the slope of the tangent line in the northeast direction, both partial derivatives with respect to the east, the partial derivatives with respect to the east direction and with respect to the north direction contribute equally. They contribute equally to the overall directional derivative in the northeast direction. I mean, that makes sense, right? If you're looking in the northeast, if you're on like a hill and you're looking in the northeast direction, the slope, the directional derivative in that northeast direction the slope of the hill in the northeast direction is affected by the slope of the hill in the eastern direction and in the northern direction, right? I mean, and they have an equal contribution. Does that kind of make sense? I don't know if you've ever sled rided down a hill or skied down a hill in a certain direction. I mean, but the overall slope in the northeast direction, for instance, is if you wanted to compute it, you look at the slope of the hill in the eastern direction and in the northern direction and do that kind of weighted average. Don't they? Wouldn't steepness in either north or east direction affect steepness in the northeast direction of the hill? And wouldn't the contributions be equal? Is this making sense? I'm trying to give you an intuitive feel for this. Is this helpful? How many are finding this a little helpful? Okay, good, Angela, good, Yeva. Yeah, I like, good, excellent, Norina. Well, Lexi, yes, you have to make sure it's a unit vector. That's right. All right, Christopher's good and Aura's good. Wonderful, wonderful. I mean, anytime we are learning difficult material, anytime we can use our intuition to help us, let's do that. All right, let me go back to the book here. So what we can do also is remember that if you have a unit vector, well, pointing in some direction, you can also represent, since it's a unit vector, you can represent the components of that vector by cosine of theta and sine of theta. Think of the unit circle, right? All of those coordinates on the unit circle can be found by finding cosine of theta and sine of theta. So the directional derivative of a function in the direction of some unit vector u can be written this way also, where a and b are replaced with cosine theta and sine theta. So let's look at an example here. Book has great examples. Example 2, they want us to find the directional derivative of a particular function, f of xy equals x cubed minus 3xy plus 4y squared, where the vector used unit direction is the unit vector given by angle theta equals pi over 6. We want the directional derivative of the function at the point 1, 2, looking in the direction of this unit vector. So in other words, if we think of this function, we think of this surface, okay, so when x equals 1 and y equals 2, we're on the surface at some z, there's the coordinates of where we're standing on the surface would be 1, 2, and then some z value that corresponds to when x equals 1 and y equals 2. And in fact, that would be equal to 0, I believe. Let me see, is 1 cubed minus 3 times 1 times 2 plus 4 times 1 squared. Hold on, I'm going to compute it. I'm going to compute it here. What I'm trying to say is this. Here's what I'm trying to say. We're looking at this example 2. Okay, this example 2. And function value, surface, is given by x cubed minus 3xy plus 4y squared. So what if x equals 1 and y equals 2? That's 1 cubed minus 3 times 1 times 2. Hold on here, I'm not sure. I think I'm, okay. Plus 4, this is fine, 4 times 2 squared. So this is 1 minus 6 plus 4 times 4. Which is -5 plus 16, and that's 11. So all right, so we are on the surface at this coordinate, 1 to 11. 1 to 11. We're on the surface right there at that coordinate, and we are looking at an angle of 30 degrees from the east. So in other words, what I'm trying to say is theta is pi over 6, which is 30 degrees. Okay, now just give me one moment here, class. One moment. I'm checking something here. I'm looking at bearings. One moment here. Yeah, so technically speaking here, okay, so this is the x-axis, y-axis, and here's our unit vector. Okay, there's a unit vector. Nope, give me that. This is our unit vector. And theta here is 30 degrees. But what this would be called, I don't know if you're familiar with this, but this would be actually north 60 degrees east. Because from the positive y-axis here, this is 60 degrees. How many maybe have heard that kind of terminology? Maybe if some of you have done a little, I don't know, boating or just, I don't know, hiking. How many have heard of these kind of, like, this kind of, I want to say it the right way, bearing, navigation type terms? Is anybody, I mean, I'm actually glad I'm mentioning this because it could come up in a homework problem, right? And you should know, okay, Mary's has seen it in astronomy and Yave has seen it a few times. So north 60 degree, okay, and in the homework too. So just, it's good we refresh ourselves. So we are on this surface, okay, standing on the surface at the point 1 to 11, and we're looking in the direction of north 60 degrees east. That corresponds to a theta of 30 degrees, or pi over 3. And we want to know the slope of the tangent line looking in that direction. Slope of the tangent line to the surface looking in that direction. Okay? All right, so let's go back to the book. So, okay. The formula, it's pretty straightforward. Now you notice that they put the answer, well, when they compute the directional derivative, the cosine of pi over 6, sine of pi over 6, they have the values in simplified, like in simplified radical form, the form that you've learned in trigonometry. Okay, so naturally the answer is going to involve radicals, square roots, right? Not decimals. And WebAssign will want that, and the exam will want that, and I will want that, right? All right, so this is the directional derivative. And now all we have to do is put in the value of 1 and 2. Let me just highlight this. So it's really quite beautiful. And there is your directional derivative. It equals 13 minus 3 root 3 divided by 2. That's what it equals. And that slope is positive. 13 minus 3 root 3 is a positive number. And that is the rate of change of z in the direction of u. It's the rate of the change of the function in the direction of u. And they have a nice picture here. So, let me see, I'm going to have to. So in this example, the directional derivative is the rate of change of z in the direction of u, and the slope gives the tangent line. They're being a little bit, they have a nice picture there. You can see if you take your surface and intersect it with the vertical plane, passing through 1, 2, 0. I want to say this the right way. Well, I think the picture is pretty clear. The function is increasing in the direction of that vector u. It is. And the slope of the tangent line at the point 1 to 11 is equal to the value that they gave above. Okay, so are there any questions on that at all? We're going to move on here, do some more, look at some more things. Okay, or is good, very good. All right, well, let's keep going then. Let's keep going. Okay. So, of course, the directional derivative, based on the formula, we can write that actually as a dot product of two vectors. One vector has the partial derivatives as its components, and the other vector has the components of the unit vector, AB. So that's nice. That's nice. And it turns out that that vector with the partial derivatives with respect to x and y, we call that a gradient vector. That is called a gradient vector. Okay, so let me just see here. Maybe I can have highlight this. Yeah, well, you know, there it is, the gradient vector. So now the directional derivative can be expressed as the dot product of the gradient vector with the unit vector. Okay? So let's look at another example here. Let's look at example 4. Okay, this is good. So in this example, they want you to find the directional derivative of a function at the point 2, -1 in the direction of this vector 2i plus 5j. So, okay, first, we're going to compute the gradient vector. So the gradient vector they show you below, you're just computing the partial derivatives, getting the components of those, and then substituting in x equals 2 and y equals -1. Now we're almost ready to compute the directional derivative, but the problem is the vector v, which equals 2i plus 5j, is not a unit vector. So what we have to do is we have to take that unit vector and, well, we have to take the vector v and divide by its length in order to get a unit vector. The unit vector u points in the same direction as the vector v, okay, but it has unit length. And at this point, we are ready to compute the directional derivative. And that's what they do. Again, the answer's in simplified, well, it's in radical form. So it looks like if we look in the direction of 2, -1, it looks like the surface is increasing. It looks like it's increasing in the direction of 2, -1. Well, I'm not saying this right. No, that isn't right. If we're at the point 2, -1, okay, well, 2, -1, and then there's some value of z, so we're on the surface, but x equals 2, y equals -1, and we look in the direction of the vector v, which is 2i plus 5j, the surface is increasing. Let me show you a picture of this. I have a great picture here. So you see this, whoops. So what they've drawn, hold on here. One moment, everybody. Let's see if I can. I think I'll have to make it a little, whoops. Okay, so in the picture here, they have the gradient vector. The gradient vector was -4i plus 8j. So all right. So you see, there's the point 2, -1. I might try to make this. There's the point 2, -1, and you have two vectors coming out of 2, -1. One is the gradient vector, and then the other is the vector v. The vector v is 2i plus 5j. Looking in the direction of that vector v, the directional derivative was computed to be 32 divided by the square root of 29. So that means the surface is increasing if we look in that direction. When x equals 2 and y equals -1, and we look in the direction of that vector v, the surface is increasing. And based on the contour plot, if we look in the first quadrant there, what are you noticing about the level curves of the contour plot? What seems to be happening as you're moving away from the origin? What can you tell me about those level curves? Or maybe a better question to ask you, based on the contour plot in the first quadrant, does it look like the surface is getting steeper, or is it getting shallower? That's right, Norina. The level curves in the contour plot in the first quadrant are getting closer together. So the surface is getting steeper. And in fact, it's increasing in steepness. So it's like going upward. Okay. So it makes perfect sense. It makes perfect sense. So are there any questions on this example? Okay. Okay, if you're good, let's keep going. So you can have a directional derivative of 3 variables too. You can have a directional derivative of 3 variables. And of course, the definitions or the formulas are just an extension of the directional derivative when you have a function of 2 variables. So you see here formula 12, directional derivative for a function of 3 variables. It's just a linear combination of the 3 partial derivatives with respect to x, y, and z. Okay, hopefully very straightforward. Let's do an example. Let's now do an example on our paper. Let me find one here. Yeah, this is what I want. And then let's just do this and kind of see where we are. I'd like to try to give you another little break here, but okay. Let me give you a moment to copy this example down. Okay, so here we have a function of 2 variables. Whoops. here we have a function of two variables. So it's a surface in space. And the surface, you can see that as x increases and y, well, yeah, we won't worry about that. But we want to know in what direction does the function f have the maximum rate of change at the point 2, 0. Okay, so now you're not being given a direction and asked to find the directional derivative in that direction. You're being asked in what direction of the infinite number of directions that there are, what direction would the function have the maximum rate of change at the point 2, 0? So this is important. This is important. You know, if you think about, for instance, avalanches, you know, you got to worry where the rate of change is the steepest, right? For the avalanche, right? I mean, that certainly would be a very important direction to worry about, right? On a mountain, if there's an avalanche, it might fall in the steepest direction. Okay, if I recall, wasn't there an avalanche recently? I think it killed six skiers. I forget where it was. How many heard this in the news? It was an avalanche, but I forget where it was. Did anybody hear about this? It was recent. No, not in Maryland, Mary. It's I think over. I don't know if it's in the French Alps or I'm trying to recall. I'll have to look it up. But yeah. So you know, knowing the maximum rate of change, you know, and the direction that maximum rate of change is important, right? Because if the maximum rate of change is in the direction of your, you know, of lodging or something, that could be dangerous, right? So there are a lot of practical applications here, but let's go ahead and let's see. So how are we going to find this? So, okay, first of all, what I do is I say, okay, well, the directional derivative is given by the dot product of the gradient vector and a unit vector. But of course, we want to know what unit vector to, you know, that to concern ourselves with. Well, so definition of the dot product. Remember, if you go back to section 9.3, the dot product between two vectors is equal A and B, and maybe I mean I want to be careful on my notation here. I don't want to use A and B too much, but if you had like the dot product of vectors C and D, that's the length of C times the length of D times the cosine of the angle between the vectors C and D. So yeah, no problem. We have a gradient vector and we have a unit vector. Here's the dot product, but the length of the unit vector is just 1. So the directional derivative, okay, is equal to the length of the gradient vector times the cosine of the angle between the unit vector and the gradient vector. But where would this be maximized? Where would this be maximized? Well, it depends on cosine of theta. Where's the cosine of theta the greatest? Because the gradient vector is already, that's computed, that doesn't depend on the unit vector at all, right? But the cosine of theta that varies based on theta, and it's maximized when theta is 0 degrees. So this means then that the directional derivative is maximized in the direction of the gradient vector, because the cosine of theta, the biggest value it can take is equal to 1. So that means if you want to find the direction in which the function has the maximum rate of change at a point, compute the gradient vector. That's what that means. So it's a very special vector, a very special vector. So, okay, so when x equals 2 and y equals 0, the gradient vector equals 1, 2. Okay, it equals the vector 1, 2. And so the function, our function, is going to increase fastest in the direction of 1, 2. And the maximum rate of change then would be just the whatever the length of the gradient vector is, which in this case equals root 5, because the length of this vector is just the square root of 1 squared plus 2 squared. Make that a little nicer here. Hopefully everything's making good sense. So this actually, the example we're doing is example 6 in the textbook. And what I've done is I've put pictures up for you. I've taken the book pictures and put them on the next page. So if we're good here, let me go to the next page. Are there any questions so far? Okay, yay was good. All right. So a few pictures here. Okay, and maybe I will highlight. One moment. Let's make this a little, yeah. So the gradient vector, remember, was equal to, had x component 1 and y component 2. So starting, we're at the point here, we're at this point P. Hold on, get this off. Hold on. We're at this point P, and P, you can see, P has coordinate 2, 0. So again, we're trying to visualize this surface using a contour plot. But this contour plot has the gradient vector superimposed over it. So the gradient vector, the blue gradient vector, points in the direction of maximum rate of change when you're at the point 2, 0. Now they've drawn here, they've drawn also another vector. Hold on here. They've drawn another vector, PQ. And let me ask you, which, if you were to like say, so in this case, let's say you're a mountain climber and you're climbing up this mountain and you're at 20. You're gonna choose the direction. You can either choose direction PQ or the gradient vector, the blue gradient vector, which is going to be based on the level curves of the function that they're showing you. Which directions would this mountain, this surface, be steeper in? The direction of the gradient vector or the direction of PQ? That's right, Lexi, the gradient vector. The gradient vector. That's the direction of steepest ascent. That's the direction of steepest ascent. Okay. And what do you notice about, like, if you look at these level curves? Another thing you might want to notice here that's kind of interesting is if you look at these, I'm probably going to have to, if you look at these level curves here, what seems to be true about the angle between the gradient vector and these level curves? Does there seem to be, like, if you think about what I'm talking about is, I'm talking about, I want to use my colors carefully here. I'm talking about like this angle here. That's not actually, yeah, it's orthogonal. That's right, Lexi. So let me just see if I can make this. Let me do it again here. Hold on. Okay, there's the gradient vector. And here's the level curve, okay, to the gradient vector. And that angle seems to be 90 degrees. And that seems to be the case, by the way, if I have another level curve here, and I look at the angle between the gradient vector and the level curve, that also seems to be 90 degrees. And that's no accident. That is no accident. We're going to prove that tonight. But they mention, notice from this figure 7 that the gradient vector appears to be perpendicular to the level curve. Well, I want to be a little bit careful here. I probably didn't say it right. I'm going to take that back, what I said. I should have, I didn't say it right. I didn't say it right. No, we're not, well, hold on here. I want to be very careful about what I'm saying. No, I didn't say that correctly. I want to focus on one level curve. If I can draw it. I want to focus on one level curve. So here's the point P. The point P is at 2, 0. That's what we're interested in. Here's the level curve. Okay, there it is. And what you should be noticing is that the angle okay, hold on, I'm going to draw one more thing here. Yeah. Okay, so what I've drawn in the picture, okay, what I've drawn in this picture is I've highlighted the green level curve, okay, that passes through the point P. And I've drawn the blue gradient vector at the point, from the point P. And also I've drawn a red tangent line. Okay, this is a tangent line. Okay, to the level curve at the point P that has coordinate 2, 0. The angle between that tangent line and the gradient vector is 90 degrees. It's orthogonal. But because it's orthogonal, we can say that the gradient vector appears to be perpendicular to the level curve as well at the point 2, 0. So the gradient vector is perpendicular to the level curve at the point 2, 0, because the level curve is, you know, the tangent line to the level curve at the point 2, 0. You know, that's the level that, well, I hope I'm trying to say it the right way, but at the point 2, 0, the tangent line and the level curve have the same slope. So that's why the gradient vector is perpendicular to the level curve. The gradient vector at 2, 0, or no, the gradient vector for the function at 2, 0 is perpendicular to the level curve at the point 2, 0. Okay, does that make sense? I'm trying to phrase it just very, very carefully. Okay, wonderful, Angela, wonderful, wonderful. And that's a very important concept, a very, very important concept. Let me just see if there's, yeah, so the level curve, I'm going to actually show you why right now, because I think it's a good time to do it. So the level curve, remember, this level curve, trying to say everything properly. The level curve, which I've drawn in green. Notice it's also a space curve. It's also a space curve. And a space curve, you can draw a space curve with a vector function r of t. So what we need to do is show that we want to show that the derivative vector of r of t at some time of t, and that time t, this time t, corresponds to when you're at 2, 0. If we take the dot product of that derivative vector, which is the slope of this tangent line here, by the way, well, no, the derivative vector, I want to say this the right way. Yeah, this is fine. We want to show that the derivative vector, the dot product of the derivative vector with the gradient function, okay. I'm not saying this the way I want to say it. I'm going to just go on the next page here and do this. I want to show why this is a right angle, okay? So let me go to the next page here because I'm getting I'm trying to be very exact, but sometimes when you're very, very exact, you know what I'm saying, right? We're fine. So the level curve, the green level curve, okay, in that picture can be represented by a function of x and y, and you set it equal to k. That's a level curve, right? But the x and y functions, the x and y can be thought of as also as functions of time if you want. Okay, you can make x and y a function of time. You still have a level curve because the function of x and y equals k. Now, if you were to differentiate, if you were to take the derivative, I should say, hold on. If you were to take the derivative of both sides of this equation with respect to t, well, on the right side, you get 0. But what about the left side? Well, function of x and y, based on this, we have a function of x and y, but x and y are functions of t. So we can utilize the chain rule. And so on the left-hand side, what we have is the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. That equals 0. Okay? These aren't dot products. These are just times here. But we can write this as a dot product. We could write this as the dot product of the gradient vector with the vector whose components are the derivatives of the components of x and y. And so this proves that the gradient vector is perpendicular to the derivative vector. The gradient vector is perpendicular to the derivative vector at time t. So what you have then is, again, the level curve, okay, yes, the level curve can be represented as a function when the function of x and y is equal to k, but also the level curve can be represented as a space curve also. That's also the level curve. So at a point, at some particular xy value, the level curve would point to that coordinate for a certain value of t. And the gradient of the function at that point is perpendicular to the level curve at that time t. But essentially, that's just saying that, well, the gradient of the function at that point, at that coordinate xy, is perpendicular to the level curve at that coordinate xy. And that's why you are, hold on. That's why in the example we looked at, hold on. That's why you're seeing, that's why you see the right angle here. It's an extremely important concept. And I just, that's why I gotta use my that's why you're seeing this right angle here between the level curve and the gradient at the point 2, 0. Okay, does that make sense? Does that help you feel comfortable with that very important result? We're gonna use that when we get into Lagrange multipliers in our next class. We're gonna need that result. How many think this is absolutely cool, by the way, what you're learning here? Okay, Angela's liking it. Norina, wonderful. Okay, good. On that note, I'm going to stop the recording, and I'm going to let you work a little bit. Matthew's liking it. Yeah, give a thumbs up if you're liking it. I actually have, some subscribers. I take these videos and put them in YouTube and to get the closed captions on them. And I think I have some subscribers in YouTube. Maybe it's kind of interesting. I guess some other folks like my videos too. Well, that's cool. That's cool. Yeah, that's good, Mary. Yeah, I like that. That's fine. All right, I'm going to stop the recording. Excellent.